Hello and welcome to a video lecture on rotational dynamics. In this, we're going to go through looking at the aspects of what happens to an object as it begins to rotate and applying this rotation to concepts that we've already talked about, including Newton's second law, conservation of energy, and conservation of momentum. So we've talked about torque, and a torque is any force applied at a radial distance away from an axis of rotation that causes an object to rotate. We've dealt with linear arms or radial arms, and we understand that the torque needs to be applied perpendicular to that axis of rotation, or so to speak, the line of action here, in order to generate the maximum amount of torque on this. And what we'll see is that this torque actually causes a rotation for that. And we've seen that and it causes the object to change its rotational speed. And so we have a torque is the force multiplied by the radial distance away from the point. So for a very small radius, then there is a small torque. For a larger radius, there's a larger torque. Smaller force, small torque. Larger force, larger torque. But pretty straightforward, we've seen this before. Now, torque is a vector quantity, and in this sense, it follows the right-hand rule. It doesn't necessarily have direction in terms that we've talked about before, as in saying left, right, up, or down. And the reason for this is because we're talking about an object rotating, and this gets a little bit confusing. I like to mountain bike a lot, do it often during the summer. And if you look at this mountain bike picture here, person in a race, you would ask somebody sitting on the right-hand side of the course as we're looking at the picture, and we'd ask them to say, what direction is the wheel spinning? And the guy would say, oh, well, it's he's moving forward, so it's rotating counterclockwise. And then you'd ask somebody standing on the left-hand side of the course as we're looking at the picture, and you'd ask them, what direction is the wheel spinning? And he'd say, oh, no, it's moving clockwise. And so this is where we get into a torque. Now keep in mind that there's a force being applied on this wheel, and it's going to cause it to rotate. In this case, it's the friction with the ground that's causing the wheel to rotate as it moves forward. And it depends on the distance, that radial distance away. The right-hand rule follows, and if you want to just kind of imagine, you stick your hand in terms of the radius, and then you curl your fingers in terms of the direction of the force. The torque is positive, so to speak, if it's increasing the rotational speed. And a torque is negative if it decreases the rotational speed. So, and we'll use this right-hand rule and then we'll go over it in class. And we'll come back to it actually quite a bit when we talk about electromagnetism and the force applied on a moving charge. But the idea here is that torque can either increase or decrease the rotational speed of an object. All right. Inertia is an object's resistance to a change in motion. And the same idea holds true for a rotating object. For a rotating object, it depends on the mass and how hard it is to rotate that mass. It's based really on the relative distribution of the mass, the mass relative to the axis of rotation. So if the mass is really close to the point of rotation, that axis of rotation, it's not really hard to rotate it. But if it's farther away, it's going to be much harder to rotate that object. If you're in your house right now or somewhere there, grab, say, a broom. You're going to make fun of me because I say broom in a certain way with the O's and all that. Everybody gives me a hard time. But grab a broom and grab it close to the bottom, to where down near the bristles are, and try and rotate it. And you can kind of spin it pretty easily in your hand. If you grab it further away, far up the handle, almost at the end, it becomes a lot more difficult to rotate that object. You need to apply more of a force to rotate that object. So I have a physics stand here, a lot of mass right here, long radial arm extending from it. Now, When the mass is close to the axis of rotation, so I grab my hand close to the mass right here, it's really easy to rotate it around. Easy to spin, can move it around like that. As I move my hand away from the mass, or the mass away from my hand, depending on your point of view, now it becomes a little bit more difficult. It's harder for me. I need to apply more force or a greater torque overall to get this object to rotate. And as if I step back here a little bit, it actually takes me fully 2 hands to be able to rotate this object all the way around, because the mass is so far away from the axis of rotation. It takes a greater torque to cause it to move around. And this is where this idea of moment of inertia comes in. Here we just see the idea that for multiple different points of mass, we have the sum of all the individual mass particles based on their distance away and the axis from the axis of rotation, and that gives us this idea that we call the moment of inertia. And this is really just analogous with mass as we've talked about it before, but now we're talking about it in terms of a rotation away from a point of an axis of rotation. So, what does this mean? This means that every type of object has a different moment of inertia. These are all sorts of different objects here, and we'll start in the upper left-hand corner. A hoop is the most simple thing. It's a bunch of points located around the outside at a certain radius away, and it has a moment of inertia based on the mass of that hoop and the radial distance out there. And this is assuming that that hoop is a very thin hoop as it goes out. And there's all sorts of different objects here. And as you go down here, you have A, B, C, etc. Couple of things to point out: that C refers to a disk. It doesn't matter that length in this case, because it's rotating the axis is through the middle of this cylinder or this disk here. And another one to point out here is G, down here at the bottom left, is a spherical shell, and it should be a shell about any diameter, but that means it's a hollow inside. It's kind of a little, there's some typos within here. But these are different moments of inertia, different objects that have moments of inertia. Please look in your textbook for a little bit more thorough example if you have a hard time seeing it on the video. Alright, I hope this video was helpful in understanding moments of inertia. Make sure to look in your textbook for the table in chapter 9 on the different moments of inertia, for the moments, as we'll say, for each individual object. They all are different, and we'll look at them more tomorrow in class. Make sure to write down any questions that you have in your notebook, and please come in and ask questions, because this can be a confusing topic as we go forward here. But make sure to really write down any questions, bring them into class, and we'll talk about them then. Thank you very much, and have a good night.